I want to now introduce to you another type of analysis in sigma W. This analysis type is known as a stress redistribution. It's a special analysis type for certain cases in sigma W, and then we will use the stress redistribution analysis type to show you how you can do a strength reduction type of stability analysis using sigma and slope together. First of all, then, the concept of stress redistribution. In Q P prime space, we have the critical state line, which represents the ultimate state of the soil, or the ultimate shear that the soil can sustain. And it is not possible to exist in this space here. If we are in that space, we are overstressed. Now, physically, it is never possible to exist in that space. However, numerically, we can exist in this space, and numerically it is if a stress state point lies above the critical state line, the stress distribution in the system needs to be redistributed so that all the stress points are on or below the critical state line. So to repeat, numerically we can exist here, but physically it is not possible to exist there in the field. And as a result, numerically, we have to somehow bring this stress state point down to this level such that it is back or below or on the critical state line. And this, in essence, what we are doing is redistributing the stresses in the domain such that we want to bring the stress back onto the critical state line. Conceptually, this illustrates a path, although this may not be the actual path, but let's represent this by a delta sigma tensor. And it is a stress tensor representing the amount of the overstressing. Sigma W computes nodal forces. If there's an element here, sigma W computes forces on each element at the nodes, and these forces are applied to each element such that the delta stress here is removed and moves us back onto the critical state line. So the whole point is to redistribute the overstressed portion of the stress, and what it really means is that neighboring elements then must pick up the stress that was overstressed in an element. And for those of you interested in the equation, the forces are computed using this equation, where B is the gradient matrix transposed multiplied by the stress stress tensor gives us the forces at the nodes of the element, and when we apply the forces, then the stress is reduced in that particular element, but it means then that the forces on the nodes of that element result perhaps in stress increases in neighboring elements. So this is a pictorial summary of what we mean by a stress redistribution. There are various reasons why we numerically get overstressing. Some of the reasons we get overstressing in a numerical analysis is because we have used a linear elastic model. A linear elastic model does not consider the soil strength, and therefore overstress states are computed when we use a linear elastic constitutive relationship. There are other reasons why we may experience real overstressing in the field. For example, a sudden increase in pore water pressure due to earthquake shaking, for example. The increase in the pore pressure reduces the effective stress and therefore reduces the strength, and so that momentarily we might find ourselves that some portions of the embankment, so to speak, are overstressed. Along the same vein, in an earthquake analysis, a loose sand may have a collapsible grain structure, and when the collapsible grain structure collapses, there is a sudden strength loss, and this manifests itself in perhaps loss of global stability, but often it is a strength decrease, and this strength decrease manifests itself in permanent deformation. So in some cases, yes, overstressing is purely numerical by the type of constitutive relationship we have chosen, but there are field cases where there may be a reduced strength, and by having an analysis type in sigma, such as the stress redistribution analysis type, we can look at field cases where there has been a true strength loss for whatever reason, and look at the associated deformations related to the strength loss. We can use this type of stress redistribution analysis for another purpose, and that is to do what is known as a strength reduction stability analysis. In this approach, it is assumed that the soil is artificially reduced. There are other reasons as to why we may have overstressing. Like in a strength reduction stability analysis, we may have an assumed strength reduction. The stress redistribution type of analysis can also perhaps be used to simulate the slow movement of a soil mass to impose a stress on a shear key wall, for example. So here we see in sigma W our analysis type. We have a special analysis type called a stress redistribution analysis type. I will illustrate for you here the use of the stress redistribution type of analysis by doing a strength reduction stability type of analysis to look at stability. We can open up file SIG09. Before we open up the file, here is the thinking in a strength reduction stability analysis. The soil is weakened. The soil is weakened until the slope fails. Notice that fails is in quotation marks. The problem is that it is not easy to define what failure means, but generally the thinking is that failure has been achieved when the solution is non-converged, or it is impossible to get a converged solution, or the movement has become excessive. And as we will see in a few moments, it's difficult to define what excessive means, and sometimes it's even difficult to know the exact point of non-convergent. Nonetheless, these are the principles that are used in this type of an approach. So we talk about a strength reduction factor, and the strength reduction factor, when we reach failure in quotation marks, The strength reduction factor at failure represents the margin of safety of the slope, or the factor of safety of the slope. When doing a strength reduction type of an analysis, we need to do an elastic plastic analysis such that we can accommodate overstressing and do the redistribution of the overstressed amount to bring us back onto the critical state line. So the definition of the strength reduction factor is tan phi prime divided by tan phi prime at failure, and cohesion prime and cohesion prime at failure. So here is a table of the parameters that we're going to use in the strength reduction stability analysis, starting with a base case where the effective friction angle is 28 degrees and the cohesion is 5 kPa. And we can think of that as a strength reduction factor of 1. In other words, the strength is not reduced at all. Now, it is always useful to put the strength reduction stability analysis in the context of a traditional sigma slope analysis. And when we take our base strength from the sigma analysis into slope W, we compute a factor of safety at 1.56. Then when we have a strength reduction factor of 1.2, this is C prime, phi prime, C prime, and taking those stresses, we get a reduced factor of safety and so forth. Ultimately, what I did is I took the factor of safety from the sigma slope analysis for the base case and used that as a strength reduction factor. And when I use that as a strength reduction factor, then this is phi prime and this is C prime. In GeoStudio, here is SIG 09, and as you will note here, there are a whole series of analyses. To begin with, we set up the state of stress in the ground when the natural slope, so to speak, and then we look at using slope W, do a factor of safety before any strength reduction. A sigma analysis with a strength reduction, and then a slope analysis with the same strength reduction. And so sigma, slope, sigma, slope, sigma, slope, and then finally sigma and slope. Looking at the in situ case then, like in other examples, I won't go into any details here. We are doing an in situ type of analysis to set up the state of stress before as a starting point for the analysis. Then we look at the factor of safety based on our in situ stresses, and we see that we have a factor of safety of 1.56 with no strength reduction. Moving along then to the first strength reduction, we have reduced the strength by a factor of 1.2. Back into this fine view under key-in materials, we have created materials, different materials with different strengths. And these strengths here, C and phi, have now been reduced from the base case by a factor of 1.2. All other parameters are the same as they were for the base case. Another material with a strength reduction factor of 1.3, another material with a strength reduction of 1.4, another material with a strength reduction of 1.5, and the final strength reduction, which was the original factor of safety, we are back to our strengths that were reduced by the original factor of safety, 3.2 and 18.78. So for each of the cases then, we have first of all a strength reduction, and here is the deformed mesh at a strength reduction of 1.2, and then using the reduced strength we get a factor of safety of 1.3. Then going on to the next Six Sigma analysis with a reduced strength of 1.3, we begin to see a slightly larger deformed mesh, and the factor of safety is now 1.196. A strength reduction of 1.4. We're beginning to see more movement as a result of the strength reduction, and a final strength reduction of 1.5, and then our last strength reduction of 1.564. And so here is the accumulated deformation due to the artificial strength reduction, and the associated factor of safety now is close to 1. So in each case, going back to the defined view, for the sigma analyses, we selected a stress distribution type of analysis. Stress redistribution type of analysis. And it is part of the list here. We selected stress redistribution as our analysis here. So that is the procedure that we've used for this strength reduction stability analysis. I will just now summarize the results in a PowerPoint slide and in an Excel spreadsheet. So here then is a summary of the results. Now, if all you had was sigma, then this would be the only information that would be available to you. And we were still able to get a converged solution at this point here. And what I have done here is plotted the Crest settlement or the Crest movement. You can see that it is difficult to know exactly where we have failure if all you have is the sigma results. Where is the point of excessive movements? We obviously see that the movements are increasing rapidly as we approach the point of loss of stability, but it's not easy to say exactly what the factor of safety is. The advantage of having slope and sigma is that we can also compute the factor of safety at the same time. This is factor of safety scale here, and notice that with no strength reduction we had a factor of safety approximately 1.56. The factor of safety decreases as we reduce the strength, and when we reach a factor of safety of 1, interestingly enough, we get the maximum reduced strength. But this is only available because you can use the sigma W stresses and slope to compute the factor of safety. And this is one of the great advantages of the product integration in GeoStudio. You are not only left with this data, you also have this data, and the two combined together makes it possible to talk about deformation as a result of strength loss, but it also makes it possible to talk in terms of a factor of safety and to more definitively define the point at which we reach a factor of safety of 1. To those of you who are interested in our Quake W detailed examples that we ship with the product, we have a case history that is called the San Fernando case history. And in this case history, if you care to go to the detailed example and study the example, there was some liquefaction at this dam, and the liquefaction resulted in a sudden strength loss, and we have used the stress redistribution type of analysis to look at the post-earthquake permanent deformations. The liquefaction caused some strength loss, and it's a perfect example where a stress distribution is very, very valuable because it allows us to look at the deformation that is associated with a strength loss. Again, you can go to the Quake W detailed examples if you're interested in more information on this case. A commentary on the strength reduction stability approach. Our view at GeoSlope is that it is better to integrate sigma and slope when you want to talk about stability. It is more difficult to look at stability if you are going to use sigma alone. We believe it is much better and much more informative to combine sigma with slope when we want to talk about stability. So when we want to talk about stability, we should use both programs. Now, if there is truly a strength reduction in the field, then the stress redistribution type of approach is, of course, extremely valuable when we want to look at deformations, and, or in other words, as we have noted earlier in this workshop, looking at serviceability. In summary, we recommend the combination of slope and sigma for stability. If we want to look at serviceability, then we can do that with sigma and the strength reduction type of analysis. I have given further discussion on this topic in a paper called Limit Equilibrium, Strength Summation and Strength Reduction Methods for Assessing Stability, and this paper is in the Papers of Interest folder. It's on the CD for those of you who have interest in more details on this. To re-emphasize the point, and returning back to our discussions in the introduction and on fundamentals, we talked about the difference between stability and serviceability, and going back to the discussion at that point, sigma is primarily all about serviceability. Yes, we can use it to look at stability, but it should be done in conjunctions with slope. And let's remember that what we said at the start of this session, this workshop session, is that the main question that we want to answer: will the deformations be within limits such that the structure can continue to serve its intended function? And as we have said several times already, we recommend that you use sigma computed stresses in slope when you want to talk about stability. This then brings us to the end of the workshop, Sigma W workshop session 1.